Welcome back. I'm going to assume some prior knowledge or some working knowledge of the things that I've discussed on my channel and on my blog, JZ Dynamics, at Blogger. Let's just get it on with it. Assume we have a complex, a two complex, with a graph that encodes the intersection information. So it's a finite connected equal length graph, and we can prove that it's equal length if we want to, and that follows from reasons of symmetry of how we're actually constructing this object, mathcal I, which was done, recall, being an geometric optimization procedure, where we take this cube and we perform an F completion on the cube, right? So the F completion, remember, is like you take a vertex pair and it's connected via diagonal, and we're just going to take all, say, codimension 1 smooth surfaces between these that collapse to these vertices on the boundary. So they're basically they're nested, but for the interface construction, the reason it's called the interface construction is because we're gonna do some optimization here with the surface. So we're gonna make sure it's a surface with constant Gaussian curvature, okay, greater than 0. And it's a surface of revolution, and the cone points are incident with these two boundary vertices of the cube. We're going to maximize the volume of the surfaces, and we're going to basically solve this optimization problem simultaneously across all 4 diagonals. So we get 4 surfaces geometrically aligned or configured in the cube. And it doesn't have to be a cube. You could choose like a different shape, a different polyhedron. But the cube is most natural, I think, and it is the sort of the prototype that I work with. So we get a complex of these surfaces, 4 of them, if you can imagine, kind of like a stellated octahedron, but smooth, still self-intersecting. And you might be able to see that we would get a graph along any coordinate slice. Say this is, if this is -1 to 1 cubed, so if that's the cube centered at 0, the origin in R3 Euclidean space, then like this, these cone points would each point into a unique octant into this R3. So you can imagine, right, that forget this point right here, but let's say this is say z equals 0, or the coordinate planar slice is equal 0. We're gonna get so the intersection. So here's the complete. If we slice with a plane, we're gonna get this oval type shape for 1. Now when we add, so this is going to be intersecting like that, when we add the other one to come from this angle, we're going to get this And so the graph, so there's two different concepts here. When we, the outer part is the intersection, the pairwise intersection graph. So this encodes where the surfaces pairwise intersect. Now this interior square graph here is when you slice the entire thing by a plane, a plane. So I mean, I'm more concerned with this one for now, but we can also include this if we want to. This interior inner cycle. So this is as you can see 1, 2, 3, 4. And yeah, you'll have to believe me, like when you take this and you copy it, do the other slicing planes on top of it, it will be for the outer graph, the outer shell on this complex will be 4 regular, and it'll be like an octahedral skeleton. All right, so it's a bit of background. All right, so now we kind of want to get into, we have this. So we have the structure, mathcal I gamma with its graph with its pi group, and so we know what this is. It's a 2 complex formed from these kind of cone surfaces, and they intersect and to form this graph, this symmetric graph. And then we have the piecewise isometry group with some slicing, some Rubik's cube kind of deformations on this object that preserve the object because we're not. It's not linear. It's not a linear mapping, but it does preserve the surface. So we're gluing back the surface to exact same shape and symmetry. So we're not losing anything there. But the act itself, by slicing and turning, permuting, it's not a classical linear mapping here. So, but we can look at like the group of all the piecewise isometry moves, and which group it forms, and see what's invariant. And this is kind of related to scissor invariants, where you're slicing up a cube, or you're slicing up you tile a space and then you permute. Say you tile you have to triangulate maybe the Euclidean plane, and then you slice out triangles out of that and permute them in different, rearrange them different orientations and glue back. You can look at dynamics and dynamical systems, what goes on there, and that's very fruitful. So we basically know all these pieces individually, and in some sense together, how they relate to one another. But say we can also say that, for example, that fixing labeling the elements in certain ways gives us different PI groups. So what we'll do is we'll just fix all these things. So this is fixed. We can build that. This is a finite skeleton. Is a quantum graph, metric graph on this. So we know what that is. These are kind of canonical. The PI group, we just fix a coloring or a labeling of the cells. So if we color each basically like if we color this whole outer arc space like for example blue, and then we color the one over extending out here, we color that green, and then we one here like red, and there's 3 colors there for the one skeleton, comprising the one skeleton. So we got 4 colors for the footballs. So these guys, 4 unique colors for the footballs, and then 3 unique colors for the gamma subgraphs. So we're breaking them up to 3 planar subgraphs. So equals 7. And so we'll just fix, we won't label like the cone points or anything, as we won't label the cone points as elements or different colors. We'll just deal with the one skeleton and the two skeleton, basically. So so it turns out that we can prove that that is isomorphic with this coloring scheme. It's isomorphic to the 2x2 pocket cube group. If you're familiar with the 2x2 pocket cube group, not the 3x3 Rubik's Cube, which is more popular, but the 2x2 group, this is non-abelian. So we're dealing with a sort of non-commutative object, non-commutative group. It has order something like 2 million something. And yeah, and so we have that. All right, so there's a couple other things we can do. We can look at vectors. So we can put line bundles on, smooth line bundles on this graph, and get a notion of holonomy. And so we can also, therefore, even if we didn't have the vectors, this is a graph. We know we can put the Ihara zeta function on this graph. So when we put the vectors, we have some sort of notion of holonomy on this. We can then twist the Ihara zeta function via holonomy. So that's pretty interesting, because, what if it was all well and good to have this MathCal this geometric structure with its symmetry group, but, say we want the same group to act on the zeta, Ihara zeta, spectral data coming from holonomy twisted Ihara zetas, so we want this group to act on the vectors, essentially, and the holonomy. And the way that occurs is quite natural, is because when you do these Rubik's Cube twists, if you have a vector pointing upward, it's going to twist it to that direction. So it's basically going to permute the directions of vectors, and it's going to actually give us a geometric lens and how to look at geometric, way to understand how we can get angle deficits at certain edges on the graph or at vertices. So it can do so what we can have is like a vector here. Let's say this is like, we're dealing with like a vertex here, and we have this vertex, and say like our Rubik's Cube moves via the PI group. It can change this. So we initially had like just one vector here, but when we slice, we're gonna get two mirror copies And then basically we can rotate that away and leave this the same. So what it can do is bring the copy that's over here into the page and bring it out, and we'd essentially replace this by a copy that is going straight up, maybe. So we have that angle deficit now, and voila, we have non-trivial holonomy. If in the case that the vector went up, when we did that piecewise isometry, the vector came out and was like this, like this, and then we glued back. So we just get a vector, then it's back to its original orientation, and we get trivial holonomy. So it's kind of hard to describe there, but I hope you get the point, that this piecewise isometry group, so these elements of the piecewise isometry group, maybe delta, call them delta, these can actually induce, they can induce angle deficits or angular deficits, and twist, basically create non-trivial holonomy subgroups. So there are ways to actually make it so that the piecewise certain orbit classes, as subgroups of a subgroup of PI group, it's possible to make to construct orbit classes that leave the spectra invariant, so spectral stuff just doesn't change. And that's interesting, because then we can sort of classify like what can happen with this, and we can classify the spectral invariance of the twisted Ihara zeta function. In all possible cases, it's a finite group, so we know that this finite geometry and finite combinatorics tie the zeta down in a sense, so it can't just we know how to calculate this in a finite way. It's not infinite, so we don't have to calculate infinite possible orbit classes, or if you get what I'm saying there. So essentially that's a big picture. So now I'm going to go into some notation. We'll let P be defined to be piecewise isometry group of mathcal I, whose elements are delta actions. We will let representations be this. Let these be stratified representation space. All right, so each row holonomy representation in space of representations gives a twisted Ihara zeta, and that would be, I'll denote that zeta sub rho of U. All right, so we already know that a delta action on gamma, the graph, induces an automorphism of the fundamental group of gamma. So essentially, the delta action, so this twisting action, this piecewise element of the piecewise isometry group, it pushes the holonomy representation to another representation. So you got basically a left action. So we're gonna get a left action. Sorry, that's bad. Bad handwriting. A left action P. I'll try to write neater. Okay. Left action. Right there. With delta and so we get that, and that's in addition to whatever holonomy twist we choose to bake in, basically. So because zeta, our zeta function is functorial in the holonomy representation rho, we basically get this. We can basically conclude that P, right, P, say twisted Ihara zetas, right? So we have that with delta dot zeta rho is defined to be, let's write it down here, it's defined to be zeta delta dot rho. So for the same group, so for the same group, but it's now acting on spectral data, right? So, and it makes sense because you know, if we didn't enrich the graph, if we didn't decorate the graph, then it would be, you know, just kind of like a combinatorial rearrangement, permutation. We know what's going on here. But now that we, and now that we decorate it with these vectors, this line bundle, we have holonomy. So now it's going to, the graph is going to, the group is going to act on the enriched data, on the spectral data. All right. So next page. All right. So now we have. Now we pick the spectral stuff we care about. You know, maybe the pole set or the order of the pole at u equals q to the -1, determining degree, location of zeros in a certain radius of convergence, certain disk, or maybe the whole Euler factor multiset. You know, we can pick basically. We just pick the spectral information we really care about. So we can assign it just in general spec zeta functions map to S. And this is not the sphere, this is basically math cal S. So it represents the spectral invariant. So some spectral invariant space. It could even be, you know, just simply pole structure, you know. So So if we have that, then because P acts on the source, you can transport it like so. So spec of delta dot zeta rho equals spec zeta delta dot rho. Okay. Now here's a very nice definition, or key definition. This is interesting. And it's really important for what we've been developing is the spectral orbit class of the holonomy representation. So let me just, right here, spectral orbit class of rho. All right, so take spec rho defined to be, right, spectral spectral orbit of the holonomy. We'll take that to be delta in P in the piecewise isometry group, and then we'll have given spec zeta delta dot rho equals, all right, continue down here, spec zeta rho and braces. So this is essentially the stabilizer of the spectral invariant. So yeah, note that we have, this definition says that the spectrum, or the spectral content here. So when we act via delta action, we're gonna get the same sort of object. So it's an invariant here. And now, so we want to match the spectral group to the piecewise isometry group. So for each row, we get a subgroup. We get a subgroup stabilizer P rho spec defined to be, and I'll write it down here, brace delta in P given spec zeta delta dot rho equals spec zeta of rho, which is already, subset of P, subgroup of P. So we can package the spectral information as which delta actions fail to move the spectrum. That is a group. And it's in fact a subgroup of P. In nice cases, we will even have we'll even reflect geometric symmetries of the graph gamma. So like a big picture here is big picture here is that the big group is P, which is equal to the PI group, math cal I. The representation corresponds to action on zetas, and the spectral stabilizer is P sub rho. So it's P sub rho defined to be stabilizer E rho spec. All right, so, and finally, the orbit of rho is P quotient P rho. All right, now what we can do is compare different rhos by comparing their spectral stabilizers. So two reps in the same P orbit class. Two reps in the same P orbit, but with the same spectral invariance, live in the same spectrally rigid class. So why is this interesting? What's interesting here about this? You might be asking yourself at this point. So number one, spectral rigidity under delta. So some twisted zetas won't change their pole structure under a whole chunk of the piecewise isometry group, and those are special. Number two, so spectral breaking. Some other delta actions will change the Euler factors. For example, when you inject an angle deficit at one vertex, those will move you to a different spectral orbit. All right, number three is stratified viewpoint. When you jump strata, so when we're going from, say, U1 to GLN, the possible stabilizer, it will usually shrink because there's more data, which implies fewer symmetries. So that gives us sort of a nice story, a richer structure group, and finer spectral partition of the piecewise isometry group. So just to finish off this video, the delta and piecewise isometry group, delta actions of elements of the piecewise isometry group, is already the group of legal geometric rearrangements. So when I alluded, and this is what I alluded to before, these Rubik's Cube moves, we're only allowed to slice along the graph, having the structure at any given time, and then twisting kind of like a Rubik's Cube. So we're saying like let's not look at this just geometrically and combinatorially. Let's see which of those rearrangements the spectrum notices. So it's in spirit, in the philosophy of spectral geometry, because it's like, can you hear the shape of a drum, or can you hear the delta action? So if a delta changes the twist on any primitive loop, it changes an Euler factor, so it leaves the spectral class. So here that is true. Here you can, if a delta action changes the twist on some primitive loop, it changes an Euler factor, so it leaves the spectral class. So we can organize the twisted Ihara zetas into orbit classes under the piecewise isometry group, and inside each class, the spectral data, perhaps poles, maybe even determinant degree, is invariant. The invariant classes are precisely the cosets of the spectral stabilizer subgroup in the PWI group, piecewise isometry group. Yeah, so I think that's it for this video.